very good morning, everyone. My name is Atharva, and I'm from Trinity College, Dublin. It's a great pleasure to be here at XRPL Commons. And today, I'll be talking about integrating post-quantum cryptography into the XRP ledger. So we'll take a quick overview of the XRP ledger and its current security algorithms. Then we'll address some threats faced by these algorithms and how post-quantum cryptography could be used to withstand these threats. After that, we'll take a in-detail look in how we integrated crystals dilithium, which is a post-quantum algorithm, into the XRP ledger, followed by the results and future work. So XRPL is well known for its use cases due to its key features. It is cost efficient, processes transactions at high speed, it is highly scalable, it can handle increasing volume of transactions, and its main use cases include cross-border payments, decentralized exchange, payment channels, and tokenization of digital assets. Currently, XRP Ledger supports two key types. The first one is SACP 256K1. It uses an elliptic curve digital signature algorithm over the SACP 256K1 elliptic curve. This is the default for XRPL, and this is also the same approach used by Bitcoin due to its robust security. The second type is the ED25519 Donna. It is a Edwards digital signature algorithm used over the twisted Edwards curve, or curve 25519. Being a recently developed algorithm, it offers improved performance and security, such as resistance from side channel attacks. Now, the key size of ED25519 is a byte shorter than SACP. Hence, XRPL solves this problem by prefixing that key size by 1 byte. So the key size of both the schemes would be exactly the same. Now, these algorithms provide enough security against classical attacks, but there are still some threats which these algorithms may find overwhelming. These threats are performed by quantum algorithms. A quantum algorithm is a step-by-step computational procedure carried over a quantum computer, leveraging quantum phenomena like superposition, entanglement, and interference. Currently, XRPL faces threats from two specific quantum algorithms. Shor's algorithm can solve complex problems done by elliptic curve cryptography in polynomial time. It can evaluate elliptic curve discrete logarithmic problems over both the curves, SACP and ED25519, which makes it a direct threat to modern encryption schemes like RSA. Grover's algorithm, on the other hand, may not be a direct threat, but it still has potential to evaluate cryptographic hashes faster than any brute force algorithms. For example, it can convert security of a 256-bit signature scheme to that of 128, therefore potentially halving the effective security, which would indirectly reveal the private key. So when quantum computers or the Q-Day happens, these algorithms would be a major threats to the current encryption schemes. Hence, we have post-quantum cryptography. A post-quantum algorithm is refers to cryptographic methods designed for classic algorithms to withstand the cryptanalysis attacks from quantum computers. There are currently 5 different types of post-quantum algorithms. The first one is lattice-based cryptography. The example algorithms are crystal dilithium, Kyber, Falcon. The second one is code-based cryptography, has algorithms like HQC and classic Cleese. The third one is hash-based cryptography, which has the algorithm Sphinx Plus. The other two are multivariate and isogenic based. So NIST, the National Institute of Standards and Technology, have declared Rainbow and Cyc as insecure as of 2022. So our main focus is crystals dilithium. So dilithium is a PQC standardized NIST candidate for post-quantum security. It is dependent on complex problems like learning with errors and short integer solutions. It uses fiat shimmer with abort technique, which makes the lattice-based signatures more compact and secure. Dilithium uses uniform sampling on top of this, which is easier to implement and more secure rather than its default Gaussian sampling. Moreover, it is built on Boy and Goldberg scheme, which reduces the public key size by more than half. Using all of the techniques above, it achieves the smallest combined key size and the signature size, which makes it a suitable candidate to be integrated into the XRPL. Now, let's talk about how we actually integrated crystals dilithium into the XRP ledger. The following slides after this would be are going to be like great for all you coding geeks out there. So the first step was to modify the build commands to actually detect dilithium library. And since XRPL uses CMake list and Conan for his dependency management, some necessary changes had to be made there. So this is a screenshot of the Conan file, a piece of code in the Conan file. So we named the library as dilithium 2 because we were using dilithium 2 as one of the versions. There are 6 different versions. It's 2, 3, 5, and the advanced encryption schemes for D3. Now, the main goal here was to keep the build instructions intact so we could maintain backward compatibility. And a user would just build the ledger as it's how it's been built currently, but dilithium would also be getting built along with the traditional algorithms. This is a screenshot of the CMake list changes. So as you can see on the right screenshot, we first made the CMake list detect dilithium. We included the directory. We pushed it as a library and we linked it as well. So once this was successfully done, the ledger was able to detect dilithium, which gave us a green signal to actually move on to the core functions and some necessary ancillary changes. The next step was to map XRPL's current cryptographic functions to the default functions which were offered by dilithium. So the table on the right side is the exact mapping of the function which did the same operation as XRPL's SCCP and ED. The question mark you see on the screen were the functions which were not available easily in dilithium. So we had to create some of these functions using our own logic and to match with the names of the functions you see on left side of the table. So the biggest problem right now we faced for the code base was one of the function, as you can see on the screen, called derive public key. It was used to like reconstruct the public key from the secret key itself. And since this is not so straightforward in dilithium, we had to create a new function which would offer the same functionality as the right public key. So we created that function from scratch and we named it CryptoKeeper What this would do is it would generate a key pair in a deterministic way using a reference seed, using a pseudo-random number generator or PRNG. So it would take 3 arguments. It would take the public key, secret key, and the seed. And every single time we would put the same seed, it would give out the same public key and secret key. So once that was done, this was the hardest part of that integration, to come up with the logic to do the deterministic key pair generation. Once this was done, we tried to add it as a different argument within the same function. But since the derived public key of XRPL, it doesn't really use seed as one of its parameters, we overloaded that function with just another parameter called seed. So whenever a function is called using the 3 parameters as from the third screenshot you see, the key type, the secret key, and the seed, the ledger would know that, okay, this key type is dilithium, so hence it's going to use and perform all the stuff as instructed in dilithium. We also added some key size checks, so it would be able to bifurcate between the key types SCCP and ED, since they have the same public key size and the secret key size. Once this was done, we carried on modifying the other functions to include dilithium's logic. This was a function called generate secret key, which would generate a secret key using a seed. Now, since we already achieved this functionality by using the function CryptoKeeper seed, what we did was we used the same function again. Once the key pair was generated, we securely erased the public key and we just returned the secret key, therefore achieving the same output as the traditional function. So the screenshot you see on the left was the original code of XRPL, and we just added our argument below that. So the function's name would be the same, and nothing has to be changed. Later on, we moved to this last type of function called random secret key. It's gonna generate a random secret key every single time, no matter the seed and no matter the arguments. Since SCCP and ED have the same key size, it was really simple for XRPL to generate the random secret key of these 2 elliptic curve signatures. So we created 3 different types, 3 different functions for the random secret key for 3 different algorithms. And once this was done, we sticked to the style of SCCP and ED to include dilithium as well. So as you can see on the screen, there is a function which would output a random key pair. Now, since we created a random dilithium secret key function, as mentioned in the slide below, and the derived public key as well, we kept the names the same instead of the traditional names inside dilithium's core functions to make the code look more uniform. And similarly, we modified 3 other functions which would sign messages, sign signatures, and verify those signatures as well. Once this was done, we actually introduced the new key type dilithium in the key type header file, which is intended to coexist with SCCP and EDU519, as you can see on the screen. Once this was done, we faced another major challenge of how we are actually able to process the key size of dilithium, since it is super different from SECP and ED. For example, the secret key size for these two algorithms are 33 bytes, but the secret key size for dilithium is 2,528. So that is a huge difference, and we cannot just compress it to 33. So we modified the static key size array, which would take the key size 32 and 33 for the secret key and the public key respectively to a dynamically sized buffer. What this means is it would take key of any size at the start. Once the respective functions are called, it's going to do the key type check. And if that key size matches with the key type, that's when it's going to process the function and would give out the output. If it doesn't match, it's just going to reject it, and whatever operation you're doing would result in an error. So these are the key types check in the second screenshot you see is 32, 32, 2528. We did the same thing for the public key file as well. The only difference is the size is going to be 1312, which is the public key size of dilithium. Once this was done and some ancillary changes were made, we actually tested these functions and compared how different was their nature, and if they were adding extra load to the ledger due to their enormous key size. So we classified some test cases in 3 different classes. The class A would be, we didn't really modify the test case itself. Only changing the key type to dilithium was enough to get the results and compare the 2 different test cases. Some example test cases here were the environment, the ledger replay, the secret key, and the public key test. For class B test cases, we did require some more modifications than just changing the key type. So a way we solved this was we duplicated the test case within the same file, but under a different suite, or we just duplicated the entire file in the same directory and just replaced the key type with dilithium. Some example test cases here you can find are the manifest, the UNLs, or the transaction test cases. Class C was a test case we developed entirely from scratch, and we compared all the 3 algorithms for all the operations and a full transaction process using the 3 key types. So the screenshots you see on the left side is the throughput comparison of some key operations using all the 3 key types. So from here, you can see that the throughput for dilithium is significantly lower than the traditional SECP and ED2519. Given its complexity, and the screenshot you see on the right side is the performance comparison, it's a latency comparison of the 3 key types. And from here, you can see the latency is much more higher than the traditional key types. But since these measurements are in milliseconds, even though the key type differs by a lot of bytes, it still is within the acceptable limits for a transaction. So after this, our integration was successful. And for the future work, we plan to reduce the latency and increase the throughput. We plan to achieve that using the advanced encryption scheme of Dilithium 2, which is an ongoing project at our Applied Crypto Lab at Trinity College Dublin. We also plan to do a comparison with the other post-quantum algorithms such as Falcon, which is another lattice-based scheme, and a hash-based scheme called Sphinx Plus. And we would be doing it via integrating a library called Botan, which offers multiple post-quantum schemes and a lot of good stuff. And later on, we plan to perform a extensive test using all these post-quantum algorithms and using the advanced inscription schemes for these. And then we would be comparing the results and see which scheme is more suitable for dilithium. You can check out more onto our website, Applied Crypto Lab. We have interesting projects going on there, such as post-quantum cryptography, zero-knowledge proofs, Zk ballot, and so on. With that said, I would like to conclude my presentation, and I would like to thank you all for your patient ear.
You, Atharva, I do have a question.
Hey, how's it going?
Hey, how's it?
This is all new to me, so
Yeah.
I'm gonna ask two questions so I fully understand.
Mm.
First, a simple fun question. What is a lattice-based
Right.
algorithm? And second of all, you talk about throughput and latency. What do those mean, like on the more literal scale? Because especially with throughput, I don't really understand what that meant.
Mm.
And what does that, and why do you aim to have a higher throughput? And I get the latency part, why you want to have small latency, but the throughput especially is something I don't really understand.
Right.
The meaning of it.
Yeah.
Thank you.
So, to answer your question, a throughput is a sort of measurement we do. It essentially means how many test cases were completed through a given span of time. So hence you can see here the unit for it is per second. So it's like 40,000 test cases passed per second versus 12,000 test cases passed per second.
It's like a frequency.
Yes. And lattice-based cryptography, it uses, it is based on different kinds of lattices in different dimensions. So essentially, it uses problems which would be hard even for the quantum computers, like or like quantum algorithms like Shor or Gruber to solve. So in the traditional elliptic curve cryptography, Shor's algorithm can solve these problems in polynomial time because it uses technique like quantum Fourier transform or just quantum superposition, which allows it to compute all the different combinations at the same time. So essentially, it takes time to compute one combination, but in that time, it's actually computing every single combination out there. So yeah, I think that answers your question.
So that is the difference is.
Yeah.
What would you mean by different dimensions?
For lattice-based cryptography, it cannot really use quantum Fourier transform or superposition because I'll give you an example. Let's say I am transferring some XRP to you, and sorry, Vera, but let's say Vera is using Shor's algorithm, and yeah, she's gonna take the XRP even before it reaches you. So since she's using Shor's algorithm, and let's say we're using SECP to encrypt that, and now let's say I'm giving you a test which has XRP. I'm giving you one more test which has different keys and one of these keys would unlock the chest for XRP. For elliptic curve cryptography, the problem would be to find out what color is the key to unlock the chest. Let's say you have 10 keys and all are of different color. Once Vera uses Shor, she would be able to just tell that, okay, the key is like yellow. So boom, even before it reaches you, you would see that, okay, there's nothing in here. Now, second example, we are using crystals dilithium for this. So now, when Vera tries to unlock it, she would find that there's 100,000 keys. Every key is a shade of yellow, and every key is different in size. So even though she's trying to solve it, she knows the answer is yellow, but there's just like too many answers which are like very similar to the one which she is trying to find. So that's going to make things even harder for her. And hence, these lattice-based schemes are believed to remain like even hard for quantum computers to like solve. Yeah. Yeah.
Are there any other questions?
Does this turn block validation into a much longer process? So isn't the floor for block times way higher than for other blockchains where they don't use the validation?
Say again, the last part.
Is lower.
Well, naturally, since the key size and everything's like longer enough, it's gonna be pretty heavy on the ledger. Hence, we are trying to use some advanced encryption schemes which are believed to be faster, even though their key sizes are a bit similar, or some keys are even like more. So it is a topic of research, and not much research has been done yet. And since research has not been done, the optimization process has not yet happened. So we're still ahead of time when it comes to post-quantum cryptography, as NIST has given a warning that hopefully all blockchain systems should be like quantum resistant by 2030. So I guess by 2028, 2029, people will start to think about, oh, I need to make this ledger quantum safe, but also not compromise the transaction time it takes. So we're away from that answer for a bit. Yeah.
Thank you, Atharva. It was a pleasure having you here. I suggest we take a 5-minute break, and then we'll be back for the second half of the morning sessions. Thank you.